Welcome friends, Igor is here, and in this video we will cover linear algebra applications to traffic flow problems. Many road structures can be described by so-called directed networks. The intersections of streets correspond to the nodes of the network. The streets themselves correspond to directed edges or branches of the network, and the traffic flows along the branches in the specified directions. We usually assume that all traffic that enters the intersection must leave the intersection. In other words, there is no black hole in that intersection. And this means that at each node of the network, the flow in equals the flow out. We also assume that the network is balanced in the sense that the total traffic that enters the network is equal to the total traffic that leaves the network. Let's look at an example of such a traffic flow problem. We have 4 one-way streets which form 4 intersections. So we have 4 nodes in the network which are labeled by letters A, B, C, and D. All branches have arrows which indicate the direction of the traffic flow. The numbers correspond to the rate of the flow of the traffic. Our goal in this example is to balance the network. This means we need to ensure that the traffic that enters each intersection is equal to the traffic that leaves the intersection. To balance the network, we look at each node in turn. We compute the flow into that node as well as the flow out of the node. And to have a balanced network, the flow in must equal flow out. This gives us 4 equations, 1 equation for each node of the network. Notice that we have 4 variables and we have 4 linear equations in these variables. This means we have a linear system with 4 equations and 4 variables. To balance the network, we need to solve this linear system. To solve the linear system, we first construct its augmented matrix, and then we apply the Gauss-Jordan elimination algorithm to find the reduced row echelon form of this matrix. You may want to check out this video, which explains how to do it. Now, looking at the reduced row echelon form of the augmented matrix, we see that x1, x2, and x3 are the dependent variables, and x4 is a free variable. We solve each equation for the corresponding dependent variable in terms of the free variable, and we see that there are infinitely many solutions because the free variable x4 can take on any value. However, these variables have specific practical meaning. All the variables x1, x2, x3, x4 correspond to the traffic flow. Therefore, they cannot be negative. To ensure that all variables are non-negative, we must require that x4 be between 0 and 475. Yet, we still have infinitely many possible solutions, each of which balances the network flow. Now, let's assume that part of one street is closed to repair. Let's assume that the branch of the network corresponding to x4 is closed for repair. This stops the traffic through this branch, and that means x4 is equal to 0. But once the free variable is forced to take on a fixed value, then we obtain a unique solution, because then we can uniquely determine the values of the other variables that ensure that we balance the network. Let's look at another example of a network. In this case, we need to figure out how to set up a traffic light at node B to balance the total flow in the network. And then we need to figure out what are the possible flows on the inner branches. First, let's balance the total flow in and flow out for the network. The traffic flows into the network through 4 branches, and it flows out of the network through 3 branches. To balance the network, the total flow in must equal the total flow out, and by setting up an equation for y and solving it, we see that we need to set up the traffic light at node B in such a way that the rate of flow to the north of B is equal to 600. Now that we balanced the total flow in the network, we are going to assume that y is equal to 600. let's look at each individual node at every intersection. As a second step, we need to balance the flow at each node. So we compute the flow into each node, the flow out of each node, and we set them equal to each other. This results in 4 linear equations in 4 variables. These equations form a linear system. We write the augmented matrix of this linear system and apply the Gauss-Jordan elimination algorithm to find the reduced row echelon form of the augmented matrix. Once again, we see that x1, x2, and x3 are the dependent variables and x4 is a free variable. By solving each equation for the corresponding dependent variable in terms of the free variable, we obtain infinitely many solutions because the free variable x4 can take on any value. But keeping in mind practical considerations, we know that the variables represent the rate of flow, therefore they cannot be negative. And this puts the restriction on x4. It must be a value between 0 and 700. So we still have infinitely many possible ways to balance the traffic inside the network, and by choosing any value of x4, we can compute any one possible realization of this balanced flow. If you found this video useful, please like and subscribe to help others discover this content. I hope to see you later infinitely many times. Have a good day.